Hello and welcome to T Academy. In the previous lecture we saw voltage amplifiers, and there we saw that voltage amplifiers can be represented in the form of a Thevenin's equivalent on the input side as well as on the output side. The amplifier gain is given as AV times VI, where VI is the drop across the input resistance. Now, in order to have the input voltage equal to the source voltage, in case of an voltage amplifier, we want the drop across the internal impedance or the source impedance to be 0, and this will be 0 when the input impedance Ri approaches infinity. So these can then be considered as open terminals, and no current is then drawn from the source, and therefore the input voltage equals the source voltage. At the output side, we want the drop V0 across the load resistance to be equal to AV times VI. Therefore, we don't want any drop across the output impedance, and this we can achieve if the output impedance approaches 0. In this case, the output voltage will equal to AV times VI, and VI we can see from here is equal to Vs. Therefore, V0 is equal to AV times Vs. Thus, regardless of what we connect as the source resistance and the load resistance, in an ideal voltage amplifier, V0 is equal to the gain time the source voltage. In reality, it is not possible to have an infinite input impedance and a zero output impedance. Therefore, we would like the input impedance to be much larger than the source resistance and the output impedance R0 to be much less than the load resistance. In today's lecture, we will discuss current amplifiers, and current amplifiers are given in the form of a Norton's equivalent at the input as well as at the output. That is, the source resistance Rs and the input resistance Ri is connected in parallel with the source current, and at the output resistance R0 and the load resistance RL are also connected in parallel with the source, which is AI times II, where AI is the current amplification factor and II is the current that flows through the input resistance. Now, in case of a current amplifier, we want the maximum source current Is to flow through the input resistance Ri, and we don't want this current to flow through the source resistance. So ideally this can happen when the input resistance approaches 0. That is, if we short resistance Ri, then all of this current Is will become equal to II, and it will flow through this short circuited input resistance, and therefore we would have the input current II equal to the source current. At the output, we want all of this load current to become equal to the current amplification factor times the input current. Therefore, we don't want any current I0 to flow through the output resistance. And this you can easily see will happen when the output resistance approaches infinity. That is, if we have an open circuit here, then all of this current will flow through the load and it won't flow through this open circuit. And therefore, the load current IL will become equal to AI times II. And II we can see from here is equal to IS. Therefore, the final relation for an ideal current amplifier becomes IL is equal to AI times IS. So this is the relation for a current amplifier. Now, just like voltage amplifiers, it is not physically possible to have a zero input resistance and an infinite output resistance. Therefore, what we would like is to keep the input resistance much lower than the source resistance Rs, and at the output side we would like the output resistance R0 to be much greater than the load resistance RL. So that's it for today's lecture. We have covered voltage amplifiers and current amplifiers, and in the next lecture we'll start with transconductance amplifiers. So stay tuned and see you in the next lecture.